Hello everyone, we are at the topic of MOSFETs and we are studying CMOS circuits, and today we are going to look at the NAND gate implementation using CMOS technology. So the NAND gate that we're going to look at today has two inputs, and the output is taken at this node, which is connected to the drain of Q4 and drain of Q2. So let's take a look at the truth table for two input NANDs. So V1 and V2 are equal to 0. The output is going to be at high or VDD. When V1 is 0, V2 is VDD, output is at high. When V1 is at VDD, V2 is at 0, Vout is at VDD. When both of them are high, the output is going to be low, and that's going to be equal to 0. So this is the truth table for NAND gate. Using CMOS technology, the NAND gate, two-input NAND gate, consists of two NMOS transistors, this one and this one, and two PMOS transistors, this one and this one. The input signals are connected to the gates of these four transistors. V1 is connected to gate of Q1 and Q3, and V2 is connected to the gate of Q2 and gate of Q4. The output is taken at the drain of Q4, which is connected to the drain of Q2. Let's take a look at the circuit equations for this CMOS-based NAND gate. So the gate to source KVL for transistor 1, which is this loop here, is going to tell me that VGS1 equals to V1. KVL for gate to source of transistor 2, which is this KVL here, tells us that V2 is equal to VGS2, which is here, plus minus VGS of transistor 2 plus VDS of transistor 1, or VGS2 equals to V2 minus VDS1. How about gate to source KVL for transistor 3, which is this one in here, and here I have VDD equals to VSG, which is here, plus minus voltage of source to gate of transistor 3. VDD equals to VSG of 3 plus V1. How about the gate to source KVL for transistor 4, which is this loop here? And I have the KVL written here. VDD equals to VSG of transistor 4 plus minus VSG of transistor 4 plus V2. The other KVL that we have is for this loop in here, and that is gonna give me the drain to source KVL equation, which is VDD equals to VSD4, that's here, plus minus VSD of transistor 4 plus VDS of transistor 2 plus VDS of transistor. VSD3 equals to VSD4 from this small loop in here. If I write the loop in here, is gonna tell me this is plus minus VSD of transistor 3. So that small loop is going to tell me that VSD3 equals to VSD of 4. Also, I have a KCL at this node, which tells me that ID3 plus ID4, the currents that enter this loop, equals to the current that leaves this node. Also, ID2 and ID1 are the same because they are connected in series, so the same current that flows from drain of Q2 to the source of Q2 enters drain of Q1 and goes to the source of Q1. In terms of the output voltage, I can use this loop in here, and that's going to tell me that Vout equals to VDS1 plus VDS2, or I can use this loop in here. Using the loop, I can write that Vout equals to VDD minus voltage of source to drain of transistor 4, which is the same as VDD minus VSD for transistor 3, VSD for transistor 3. So we have 4 cases for analyzing this CMOS-based NAND gate. Case 1 is when this V1 is equal to VDD and V2 is equal to 0. So I'm looking at the gate to source KVL for transistor 1, and I can write VGS for 1 equals to V1, and that's equal to VDD. This is greater than V threshold for V transistor, NMOS transistor. From there, I know that Q1 is on. So how about the next one? Voltage of gate to source for transistor 2 equals to V2 minus VDS for transistor 1. And V2 is equal to 0. From there, this is equal to VDS of transistor 1. So looking at this loop in here, I have VDD volts at this node, and this node is reference or at 0 volts. So this VDD volt is going to be distributed among this transistor drain to source of Q4 and Q2 and Q1. So VDS1 is either 0 or it has a positive value. As a result, negative VDS1 has a negative value. As a result, this is less than V threshold for NMOS, which is a positive number. From there, I know that Q2 is off. Okay, because it's off, ID2 is going to be equal to 0. So because ID1 and ID2 are the same, ID1 is equal to ID2, both of them are going to be equal to 0. So I'm going back, I'm using this one, and I'm going back to the first equation that I got. I know that Q1 is on and ID1 is equal to 0. So we have already studied the case that MOSFET is on with drain current being equal to 0, and that happens when transistor is in triode mode with VDS of 0 volts. So from there, I have Q1 being on and ID1 is equal to 0 and VDS1 is equal to 0 as well. Let's take a look at the KVL for gate to source of Q3. So for VSG3, I have VDD minus V1. That's going to be equal, because V1 is at VDD, VSG3 is going to be equal to 0. This is less than voltage threshold for PMOS, and as a result, Q3 is going to be off. And from there, I know that ID3 is equal to 0. So how about Q4? VSG of transistor 4 equals to VDD minus V2. V2 is at 0 volts, so it's going to be VDD. This is greater than voltage of threshold for PMOS. As a result, Q4 is on. Now I need to check the state of Q4, and I need to take a look at the current for ID4. So I'm looking at this one, at this KCL that we wrote for the node output node, and I know that ID3 plus ID4 is equal to ID2. Since ID3 and ID2 are equal to 0, ID4 is also going to be equal to 0. So transistor 4 is on with drain current equal to 0. It's in triode mode with VSD of 0 volts. So Q4 is in triode mode, and VSD of transistor 4 is going to be equal to 0. So I know that my output voltage is going to be equal to VDD minus VSD4. VDD minus VSD of transistor 4, that's going to be equal to VDD. So when one of the inputs is high and the other one is low, the output is going to be high.